Last up for this worksheet is topic 4, which covers similar triangles. And what you need to understand is when we're dealing with similar triangles, this is just an application involving proportions, okay? And as far as definitions go, we do have one here. Two figures, so think polygons, squares, rectangles, triangles, pentagons, and so forth, okay? Two figures are said to be similar if their corresponding angles are equal and their corresponding sides are in the same ratio. Now, I will be completely forward with you. We're only going to look at triangles in this worksheet. So we're looking at two triangles that are basically the same shape, but different sizes. So imagine you have one shape and then the other is a projection of that shape. It's in the same ratio. It's going to be bigger, but it's the same exact shape. We just blow it up. Okay. So proportions can be used to find the missing length or a missing side of similar triangles. So let's look at example 7. Example 7 says solve and if necessary, include units with the answer. So for part A, we have two triangles that we are told are similar. It says the triangles below are similar, find x. Well, what we need to understand is that, and I've kind of already drawn this out here, we have angle A in the first triangle. That's going to be exactly the same as angle D in the second triangle. Those angles are going to match. Angle B is going to match angle E in the second triangle, and angle C is going to match angle F in the second triangle. So the angles are the same, but one version of the triangle is just blown up. It's bigger than the other one. They're proportionally going to be the same though. So their corresponding sides are in the same ratio. So what does that mean? Well, we have side AB on the first triangle. It corresponds to side DE. That ratio has to be the same as AB, or not AB, AC, which corresponds to DF. Hold on, my phone is ringing. So far we have side AB, which corresponds to side DE. That ratio has to be the same as the ratio of AC, which corresponds to DF. So the ratio AB over DE has to be the same as the ratio AC over DF, which has to then be the same as the ratio of BC compared to EF, because BC and EF are corresponding sides. So BC, EF. So all of those ratios are the same, and we use that to our advantage because we know if we have two ratios that are equal to each other, that creates a proportion. We know all of the ratios have to be equal, so we use the information that we have to create a ratio with information that we know, set it equal to a ratio where we know like half the information. So we're going to create an equation out of two ratios from these two triangles. Because again, we know the ratio of corresponding sides are all going to be the same. So if we take two pairs of corresponding sides and set them equal to each other, we have a ratio equal another ratio, which is a proportion. So the information that we know without a shadow of a doubt is the stuff in green. Okay, we know this. Okay, we know this part. We know that AC corresponds to DF. So we know that 7 corresponds to 14. And what we need to find is EF. So we know that AC over DF corresponds to BC over EF. Well, we know BC. BC is 6. What we don't know is EF. So I'm just going to call it EF for now. Now, we know all of the ratios are equal. So if we take one where we have all of the information and set it equal to the one where we only have half the information, we can solve that ratio, or solve that proportion rather, and get the missing side. So we're going to solve. We get 7 times EF equals 14 times 6. So let's see, I'm going to use, well, I'll go to the calculator on here. So let's go to the calculator. We have 14 times 6. I could have probably done that on paper. Didn't feel like it. So we're going to do 14 times 6, which is 84. Okay. So we want to go back to the worksheet. So we know that 14 times 6 is 84. So we have 7 times EF equals 84. We want to get the, put 80, good grief. It's supposed to be 84, y'all. I've been making so many of these videos, my brain is starting to turned to mush. So we have 7 times EF equals 84. Well, I want to get the value for EF, so I want to get EF alone. The issue is EF is being multiplied by 7, so I divide both sides by 7. 7 divided by itself is 1. 1 times EF is just EF. And then 84 divided by 7 is 12. So that tells me this length right here is 12 units long. Okay, so again, when you're dealing with similar figures, corresponding angles are exactly the same. Corresponding sides are in the same ratio. That means each pair of corresponding sides is equal to each other pair of corresponding sides. So again, AB over DE has to be the same as AC over DF, which has to be the same as BC over EF. And we can use that idea to form a proportion, taking one set of corresponding sides that we know, in this case, AC over DF, and setting it equal to a pair of corresponding sides where we only know half, BC over EF. That creates a proportion that we can then solve. Okay, so that's one way you can use proportions with similar triangles. Another way is something like what we're going to see in part B. So these types of problems where you're dealing with shadows, they come up all the time. So a tree casts a shadow of 42 feet. So we have some kind of a tree. Let's draw it. So this is our tree, and we know it has a shadow that is 42 feet. Okay, so we know that we have some tree. We don't know how tall the tree is, but we know its shadow is 42 feet. At the same time of day, a 6-foot tall man casts a shadow that's 3.5 feet. So we have some guy. We know he is 6 feet tall, and he casts a shadow that's 3.5 feet long. So without maybe seeing it here, let me just assure you, you have right triangles. So let's draw those triangles in, let's do green. So this creates a right triangle right here. And then this creates a right triangle right here. So we have two right triangles. Let me write that better. I'm going to write it in black so you can see it better. So we have two right triangles. And in this case, they are similar because we have the sun in the same location in the sky. So it's going to cast these shadows that create two similar right triangles. Okay. So we can use this information to figure out the height of the tree, which is what we're really being asked to find. How tall is the tree? Well, we don't know. But we do know that when we're dealing with similar figures, their corresponding sides are in the same ratio. So we take what we absolutely know. We know without a shadow of a doubt the height of the man and the length of his shadow. So we're going to say that the guy is 6 feet tall and his shadow is 3.5 feet long. We know that. We're going to set up another ratio that deals with the height of the tree, which is X feet tall, and it has a shadow that is 42 feet long. Remember, when you're dealing with proportions, the only real massive condition is when you set up this proportion, your units have to line up horizontally. So similar ideas line up horizontally. We have the height of the man in the numerator, therefore the height of the tree needs to be in the other numerator. And now we have something that we can pretty easily solve. It's just a regular old proportion. So we cross multiply. We have 3.5 times x equals 6 times 42. So let's see, 6 times 42, I don't feel like jumping over to the calculator this time. So 42 times 6, 6 times 2 is 12. Keep a 2, carry a 1. 6 times 4 is 24, plus 1 is 25. We should get 252. And then I need to undo the multiplication of 3 and x, so I would divide. So 3.5 divided by itself is 1. 1 times x is x. According to my notes, we get 72, but let's double check it. So we want to take the 252 and divide it by, what did we want to divide it by? 3.5. So we want to take 252. That was the 6 times 14 or 6 times 24 or whatever it was. And then we want to divide it by 3.5 and we get 72. So let's go back to the worksheet. So we had 3.5x equals 6 times 42. We found out that 6 times 42 is 252. So we had 3.5x equals 252. In order to get x alone, we had to divide both sides by 3.5. So 252 divided by 3.5 is 72. So we would say the tree is approximately or exactly 72 feet tall. And we were able to do that knowing that if the sun is in the same spot and we have these two things standing side by side or near each other with the angle of the sun being the same, we're going to get right triangles, which in this case are going to be similar triangles, and we can set up a proportion to solve this situation. All right, so that's it for applications with rational equations.